So I'll be talking about this work which came about a little earlier, and let me just motivate this work again with some introduction. So I guess many of you might be familiar with a correlator which has been of interest recently, which is basically an out-of-time ordered correlator, which generally one doesn't look at, but it has been of interest. I mean, we will see how it is interesting, at least in our context. So there is an insertion at time t equals 0, then later on there is another operator inserted at 0 and time, and then again the same operator is inserted at time t. So it's not time ordered, so that's why it's called out of time ordered, and this is normalized, and all these are evaluated at temperature beta. And there's a conjecture.
Second argument is position.
Second argument is position. So I've kept it. There is also a dependence when the position is there, but let us just look at when the positions are kept at the same point. There is a conjecture that in unitary causal quantum field theory, if this grows at all exponentially, many times it doesn't grow exponentially, but if it grows exponentially, and if the theory has n degrees of freedom, then there's a bound for the exponent lambda L, and it's bounded by this particular factor 2 pi by beta. It's a quantum bound because actually h cross comes in the denominator, and so the bound is actually infinite for classical system. So this bound, and let us recall, I guess many people have heard about this bound, they have used it in many other contexts and so on, but let's recall some of the ingredients that went into the proof of the bound. A sort of mathematical result went into the proof of the bound. So and let me say that. So you consider this function f of t, which this has this particular property that it's analytic in a rectangle actually. Though they say half strip, but actually they mean a rectangle, because I will show you an example and then it's clear. So so this is t, and this is tau. Okay. And tau is between beta by quarter. Let's have a visualization, and minus beta by quarter, and then there is this. It's an infinite kind of rectangle, but the length is like between order 1 by epsilon log. Okay, so this is a rectangle, and it's a function which is analytic in this rectangle, and it's bounded by 1 in this entire half rectangle. Then there's a mathematical result which they prove. I mean, which can be used just from mathematical consideration. One can show that this particular derivative, and it's real at tau is equal to 0. One can show that this particular bound comes about. Okay. So for instance, just as let's apply it to this particular function. Let me just go ahead. This f of t, which is the kind of function which we'll be always getting, lambda Lt. So this is the function, and if you apply it here,
what is the justification for this particular form?
For this particular form?
This particular form of f 1 minus epsilon.
No, here is an example. Right now, here is just an example. An example which I am going to just substitute in this particular equation and obtain this 2 pi by lambda, this bound. But here is just an example. But this form comes about when you evaluate these correlators. Okay, so it comes about when you evaluate these correlators. Right now, I am just going to just substitute this thing, 1 minus epsilon lambda t inside this guy. Okay, and then we will get this particular statement. Okay. So, but okay, this particular form comes about. That's the reason you are choosing this particular form of the function. But this statement is true once we have this particular condition for any form of f, which is analytic and which is real on this line, and it's sort of bounded in this whole rectangle. So the statement is true for any form of this function. It satisfies this. Yeah.
You probably need some cutoff on the left hand side as well, not from t equal to 0, because to put the bound less than equal to 1.
Yeah.
So you can
Mod is less than or equal to 1. Yeah.
Upper line and lower line are easy, but to prove it on the left line, you need to wait a little bit. have to wait larger than the decay time.
Left line, you mean this one?
Yes, this one. This is
Yeah.
in your picture it is at 0.
At t is equal to t is equal to 0, yes.
Right, at t equal to 0. But
Yeah.
to prove this inequality on this line, you will use something like maximum modulus principle to
Right.
prove it on inside this.
Yes, okay.
So you have to prove it on the boundary. So prove it on t equal to 0 boundary.
T is equal to
Prove
0
it on
boundary,
the
yeah.
boundary, you need to wait little bit. It's not t equal to 0, you need to wait little bit more.
You mean you say that there is a small like this? Okay, maybe, yeah.
Which is
Yeah,
why
but the mathematical statement, I mean, I'm talking about this is maybe for when you apply it to a correlator, you'll have to do it. But mathematical statement is true just as on, yeah.
if you have a function
Yeah.
like that,
Yeah.
you can apply. Like
Yeah.
for this correlator, you have to
Yeah, the correlator maybe we'll have to look at it particular, a little bit ahead of the
also,
time and so.
Also, if you have space coordinates, then there
Yeah.
could be like similarity. So you have to. So this
Okay.
this bound first of all bounded by Chern-Simons scale.
Okay.
Also, you have to push little bit so that you don't cause any Lorentzian
Okay.
cut.
Yeah, so right now I'm just making it as a mathematical statement. We will come to the correlator a little bit later. Yeah. Yeah. Half rectangle, yeah. Oh, this particular. Yeah. Yeah, half rectangle.
For them, don't they just impose it on the boundaries and then they?
Yeah, they use the on the boundaries and then they, of course they have a bound inside and so on because of the fact using complex, yeah. So they use that stuff. But one of the things in their thing is that they, if you read carefully, they just make the statements, okay, and they give this an example. But they don't say that there is a cutoff here, for instance. They don't say, at least in the first part. Towards the end, they say there is some, like we have to make a cutoff. Yeah. So they say there is a cutoff there. But you see that this example breaks down, actually. It breaks this assumption, okay. If epsilon, I mean, if you can take arbitrary t large, right, and lambda L is positive, then f is of course very large. F is of course, I mean, mod of f is very large. Mod of f is very large. So there is some natural, even in this example, there is some natural thing to, but they say that you can generalize this, though they give the general proof, I mean, the proof for the mathematical statement, they give it for t equals this whole strip, but then there is a cutoff actually, which they say that you can, because it relies on mappings.
Higher order corrections in epsilon.
Or no, there is this mapping which they use is actually from from the half strip, let me call it half strip, to a circle. Okay, and then they use mappings, I mean, some properties of mapping from unit disk.
If temperature is
Yeah.
large enough,
Yeah.
then you can roughly estimate this is large enough. Look, so the horizontal
Yeah.
length is much larger than beta.
Okay.
At high temperatures, you can justify them, which is like
Okay.
the black hole phase in holographic examples.
Yeah. Let me just say that. So is usually in their paper, if you read it, they actually initially they begin with a full half strip, but then they use this map in the mathematical system, half strip to unit circle, unit disk, and then they use a property of maps from unit disks to unit disks to actually arrive at that bound. But then this half strip, they say that we can change this map. So there is a map, they have some s, z is f of t plus tau, right, okay, from the half strip. So then they say that you can modify the map so that it's a half rectangle to a unit disk, and then you can use the property from unit disk to unit disk. So they don't actually, like, if you see the mathematical proof of their thing using the Short-Spick theorem or whatever, they just use half strip. But it's
But even if it's a rectangle with finite cutoff,
yeah.
you can map that
Into a circle. Yeah. That's what they say that. But the explicit form of the map, you have to. It's a more complicated map. It will be a complicated map.
Complicated, but in this limit of high temperature or keep temperature
Yeah.
fixed, this is large enough. You can
Yeah.
land
Okay.
on their answer.
Okay. Yeah. So I have just kept it as half rectangle. That's why I call it half rectangle. Okay. So to apply this for this function, for this out of time ordered correlator, which is given.
Why did you say half rectangle, not the full?
I mean, this side is not there. This side is not there. Yeah. So to apply this to the OTO given by this, they argue, Maldison and all argue, that they have analyticity Okay, they argue that f of t is analytic because of causality of quantum field theory. And to argue for boundedness, if you carefully look at the argument for boundedness, they use properties here and here, as he was saying. They use Cauchy-Schwarz inequality. Okay. Now, this suggests, okay, that you need positivity of norm. Okay. And that is what I'm going to see. Okay. I'm trying to exploit that thing and how exactly it feeds into this thing in this statement of the bound. So, for a simple example, just to keep in mind of a OTOC which violates this, is basically something which grows 2 pi n by beta, and essentially it it violates the boundedness on the strip here, because here when it goes beyond here it violates. So if this is n is bigger than 1, it violates the boundedness property. Now what we want to do, as I said, is to study the mechanism through which this boundedness this bound is violated, and that I want to see it from this Cauchy-Schwarz that point. I mean, whether how, if that is violated, how the chaos bound is violated. So, and we will focus on conformal field theories in 2 dimensions and their holographic duals. So the positivity of norm implies that conformal primaries have positive conformal dimensions. This I suppose everybody is familiar with. So if you have some primary state, which L1 is annihilated is 0, then you can prove that by just looking at this particular state and using commutation relations, and this is the norm, you can show that delta is greater than 0. Greater than or equal to 0. Positivity of norm will be delta is greater than 0. So states when with delta less than 0 violate the positivity of norm. So one would imagine, suppose you have a setup in which the Lyapunov exponent of of this particular OTOC is evaluated in some vacuum state which is created by some delta less than 0. You can imagine maybe the chaos bound is violated, and that's what I want to see explicitly. Okay, I hope the question is clear. In fact, the norm, positivity of norm, can always be violated also by another situation which is close to this. Like for instance, if you look at n equals 2 superconformal field theories which admit U1 current, then the positivity of norm leads to a bound on primaries of delta q less than is equal to, the charge is bounded by the weight. So this also is clear. Again, it comes from the algebra of the n equals 2 supersymmetric algebra. There is some part like this, g plus g minus is something like L naught minus J naught or something. So from again sandwiching between the states, you will get such a bound. Okay. So therefore, states admitting, in fact, if it is above such case, if it is not satisfying this unitarity bound, then you would imagine that chaos bound might be violated. In fact, we found such a situation here, but though I might not have time to go into this situation, which is a more complicated situation. In fact, we found a situation here in higher spin theories. So this is the higher spin charge, and we have shown that the chaos bound is violated if this higher spin charge is, it has to be restricted by a particular weight like this, a weight of that state like this, and if it violates this particular situation, the chaos bound is violated. And in fact, this is consistent with an analysis of the Katz's determinant of these theories. If you want to show, if you use positivity of norm in a very sophisticated way, there is something called a Katz's determinant you have to evaluate. And this condition ensures the positivity of the Katz's determinant, actually. Yeah.
When you say that
Yeah.
the chaos bound is violated
Yeah.
unless this is true,
Yeah.
is it,
So this situation I'm not going to discuss very much.
Bound is greater.
Uh-huh.
You're not just saying that the unitarity bound is this greater than that.
Yeah.
This
So
is rephrasing of unitarity bound.
so that's what first we found out. We found out we found out by studying some chaos bound and so on, that such a bound seems to be there. Okay, but later, within a couple of days later, actually, these guys, they analyzed algebraically. representation theory of this thing, and they found this particular condition. And if they found a more complicated condition, but if you take the large C limit, because we studied it in holographically, we get this particular situation. So, but I won't discuss this. I will discuss the former situation in which it is this, we know that norms have to be positive. If norms are positive, and as I emphasized in the Maldacena-Stanford-Schenker, they use the Cauchy-Schwarz inequality, and you would imagine that situation when such a case happens, the Cauchy-Schwarz inequality fails, and therefore the bound should be violated.
So these are norms of all states.
A particular primary which violates
So in its multiplet, norms of all states.
In that multiplet, positive,
And sorry, I missed.
Yeah.
The second condition, the most sophisticated, the other one, the
Yeah,
one with the
yeah.
W's.
W.
What is this condition? Is Q less than delta? Sorry.
This is like an example. In n equals 2 superconformal theories, if you have this, it's just true. And similar statement we saw in a higher spin theory. Like this.
In order to get positivity of norm,
this is needed. But we saw it first using chaos bound, actually. Chaos bound.
So you produced an example.
Holographically we set up. But so we will discuss the former one here, but maybe later. I think I'll have time.
So
but
what is the difference between the?
It's the same. It's the same mechanism, but here it is just on the state itself. There is a charge state.
Okay.
I mean, so this is more like general because it's SL2 itself, just SL2 algebra. I don't need the higher spin structure or something. I just want to make it a little bit more. I mean, like just in an SL2 theory, if you have a
primary which has Q
which has
delta. Then that is going to be.
Here there's no Q. That is the thing. This is more general. I mean, it should be valid.
So in particular, those general theories where your lowest conformal dimension is negative.
Negative.
So
It should. It should. In fact, we produce a holographic example. Hopefully, something called a Polyakov-Bershadsky theory, in which there is the vacuum state has delta less than 0, and there we see it's violated. So that's what I'm going to gear towards. So CFT analysis first.
And you're saying that if and only if, as soon as this happens, chaos bound will start being violated?
Okay, so the setup we have generally is when the delta has very large C. But if you do because our correlators, we use these large C approximations of correlators. So, but we don't know, how it gets corrected when large, but presumably it should happen actually, because they are using Cauchy-Schwarz inequality in their proof actually. Somewhere.
Imagine a situation where the result is true even though the proof is
it could happen.
there are many OTOCs that we consider, right? Choice of 4 for some it may be. For
some it might not. That could be also. Here also we'll have to. There is a particular OTOs which I will set up for checking this thing actually.
The coupling, right? You have some set of states which are bad.
Okay.
But then you are calculating OTOC for some other set of operators. Depends on the 3-point functions also. If it is coupling to that sector.
But let's suppose that it is coupling. You could imagine a situation where that proof doesn't hold, but the result for some other reason. But if you find an if and only if it's somehow strong.
It's strong. So we are like seeing examples, and that's what I mean. So in fact, this configuration is quite. Usually people don't look at this particular configuration. So we are looking at the thermal cylinder. Okay, so CFT. Okay, this is the temperature. Temperature is on the circle, and we keep an operator at spatial infinities. Okay, the heavy primaries. The primaries are kept at spatial infinities. This is actually different from the situation which mostly people are familiar with, where the cylinder is temporal, and the operators are kept at temporal infinities.
This situation is like heavy states.
These are heavy states, and these are the new situation which I'm going to look at actually. This is the new situation which we look at. And but it is very closely connected to this system because it's a modular transform of that, right? So in fact, this situation in which everybody is familiar with, more people are familiar with, is the vacuum energy density is actually like the vacuum is minus C by 12, and then because of this primary, it shifts. Minus C by 12, 1 minus 24 delta by C. So it shifts. You can easily, it's an exercise in conformal field theory, you can actually check by just the plane to the cylinder map, you can check this.
Delta
Okay.
phi is
The
holographic dimension?
I mean h equals delta phi. H equals delta phi.
That's why you guys have two.
Yeah. H equals delta phi. H bar is delta phi. Okay. So what happens when the operator is a spatial infinity? It's a similar situation actually. So the best, as we discussed from the picture, you would think that okay, it's best to think about the density matrix. I mean, at least from the way you think about it. So there is a thermal state. Okay, that is this. That's the density matrix for the thermal state, and then you are inserting these fellows. Okay, at L goes to infinity. So here the operator insertions are kept at spatial infinity, and let us suppose you think about it as a limit of a torus. Spatial. So no, here now I'm going back to this picture. So no, L is this, and this is phi. Yeah. Correlator is a trace. Correlator. Yeah. So So this density matrix is the thermal state, and then I'm inserting on the thermal state this phi at infinity. This is sort of the picture of the operator we would like to have.
In order to get the density matrix, you are cutting the cylinder off, right?
Cutting the cylinder.
Otherwise, if you glue it, then it would be like taking the trace.
That's correct. Yeah. So you cut it. Yeah. So this is the trace. Yeah.
And the fact that there is this e to the power minus beta h between the two.
That's the density matrix. Yeah.
That's the density matrix, and is that specifying some sort of infinitesimal time ordering between the two? One is a little bit before the other, right?
Yeah. This has to be before that. Yeah.
Is this in some sense equivalent to turning on a chemical potential for translation in space direction? What is this operator phi?
This is the state I'm looking at. This is the state I'm looking. Yeah, this is the state I'm looking at actually.
And the real time insertions are more or less equal for these.
Yeah, the real time insertions are equal. Is equal. Yeah.
Why minus beta h is in between the two?
Because I'm looking at a thermal state. So the usual thermal state is just e to the power of minus beta h. Okay, so which you can write as summation e to the power of beta ei. I mean,
wants to know where these are minus beta h. Whether
in between.
If I think of this as cutting the cylinder, then one phi is on this boundary and the other phi is on the boundary.
Right. Yeah, that's correct. Yeah.
So it's this, the ordering that places this guy before that.
Yeah.
That forces this equal.
Yeah. You will see. I mean, practically when we evaluate, basically we'll have to evaluate traces of these guys with various insertions. Traces of rho phi with various insertions. That's what we will do. That turns out to be a correlator. Okay, we'll see. We'll see how I'll implement this. Okay, so
You can write phi at L as phi at 0 and action of translation.
You can, you want to do that.
In this sense,
Okay.
Would it be equivalent in some sense?
Yeah, you can write formally like that. Yeah, if you want to write phi L, but then you'll have to calculate the translation and so on. We'll see how I calculate this. So, okay. So at least from that picture we had, you would think that other state is a modular transform of the state, and so let us use that to evaluate the free energy of this particular configuration. So let us use that intuition first. So minus 1 by beta log trace of z, which is minus 1 by beta log trace of rho phi. Okay. Without the insertion is just the usual density matrix. And let's use modular invariant. Z of minus 1 by tau bar is Z of tau. So it constrains this free energy in this particular limit. So we are going to take this limit, okay, this high temperature limit. And if you use that, okay, so 1 by high temperature. And if you use this picture now, because it's the sums of the L naughts there. Okay, and the L naught minimum is delta phi now, delta phi. So you put delta phi here. So basically it's e to the power of 2 pi I energies, right? 2 pi I tau. But now I'm using minus 1 by tau here, okay, and L naught minus c by 4, and then L naught minimum is this weight of the zero temperature ground state. Usually it's zero temperature ground state, but now it's the delta phi, okay. and if you put that in, you get this free energy. Okay, so this is the free energy. So it gets shifted. We will arrive at it by another means also. But so this is the free energy as tau goes to I 0 plus, basically high temperature limit. It gets shifted. The free energy gets shifted here by this manner. So the result for the free energy has actually, we will come again, we will arrive at this at a different way, a more calculational way.
The one was Cardy's formula.
Yeah, one is the Cardy's formula.
And this is the shift.
This is the shift of, because this has. Okay, so this we can interpret it in two ways. Okay, so first naive way was this is not, of course, is that we can shift. We can say that somehow the theory has an effective central charge C minus 24 delta phi, or the value of the temperature shifts to a new effective value like this. Okay, but this is unfavorable because you don't expect short distance properties of this theory to change. So you would expect, in fact, our probes will actually keep the short distance of central charge to be the same. So you would actually favor this interpretation, and we will see that. Yeah.
You look at the OP coefficients and you want to preserve the original one?
Yeah, the stress tensor is a short distance property. Central charge is a short distance property, and so the central charge doesn't change. It's just a matter of TT thing very close by, so we can read out the central charge from there, and so it shouldn't change the central charge, and therefore we go to this shifted effective interpretation, and I will give more evidence for this as we go ahead. The torus, but with the limit, cylinder limit. With
where are the insertions on the torus? Because
torus,
this is going to be long, and also the.
Yeah, so it's a limit. I think it's
opposite to each other, or are they colliding?
Yeah, the torus. I can't think of the picture of the torus very well, but with the phi insertions, I don't know how to think about it.
Phi insertions at
particular points. Yeah, particular points on this circle. Yeah.
So now when you close it off, are these?
Yeah.
I'm just asking, is it L by 2, L by 2, or L?
It's L by 2, L by 2. Yeah.
So
yeah.
This length of this spatial cycle is L.
Spatial cycle is L. Yeah.
And then they are just opposite to each other on this circle?
Yeah, they are okay. So they are at. So suppose I. Yeah, torus. It's because I actually look at the cylinder all the time actually, but I'm thinking of it as a limit. Okay, though I have used modular invariance to get it, I will get this result in another way soon. But let me just say, so we have sigma and tau. Sigma is this direction and tau is this direction, which is so we actually look at something like it doesn't matter when you take limits. It doesn't matter where the tau is if you see it. So it is infinity tau, and one is at minus infinity tau on the thermal cylinder. The coordinates on the thermal cylinder is sigma and tau, say, and tau is, of course, on the thermal cylinder tau is periodic. Okay.
That means they would collide at the back, right?
Huh?
They would collide at infinity.
It collided. If you identify them. Yeah, actually that, this picture of the torus, I'm not, it's.
You are getting the answer from the torus part.
Yeah, I will get it another way also. I will get it another way. So even though,
the fact that
yeah,
it's working,
yeah, it's working. Yeah,
just want to see
how it is working.
Yeah.
Yeah. So here we don't use it very much. Where exactly it is? No, here we just use the relation between this cylinder, this one, and then L naught. We use the fact that here the minimum weight is not L naught is equal to 0, but it is delta phi. You had a question.
Can you interpret these boundary operators
Yeah.
as part of your definition of the Hamiltonian, like adding some boundary action?
Boundary action, I don't know. Maybe let us go. It actually is, if you're evaluating these traces, let's call this state as rho phi. Okay. The prescription which we will wind up finally is like, suppose I want to calculate, which essentially we want to calculate with various other operators, some O1, O2, and so on this particular state. So it will be basically, it will be correlators of O1, O2, and dot dot, with the phi at infinity, phi at minus infinity. So these kind of correlators, it's normalized with. So this is the final statement we'll arrive at. Actually, we will arrive at these are the correlators we'll have to evaluate. Yeah.
So in previous transparency of free energy will be proportional to the length of the cylinder, right?
Yes, yes, it comes out. You can see it comes out. Tau is this.
Right.
I beta bar.
That's what I'm finding intuitively odd, that you put
Yeah.
insertions at points, and yet you get an extensive change.
Yeah.
If that created some line operator, that would be acceptable. But that points make an extensive change sounds odd.
But okay, let me give the calculation another way. So maybe it is more clearer that way.
Yes.
So let's see. So I'll give it soon actually. So the presence of so this is what I was saying. It should not interpret the state by the therefore we therefore interpret this as this, and we will give more justification for this. But so let us see it this way. Let's probe the state further. This is another way of doing it. So this is how actually we found out. So what we take is we take that particular state and evaluate the stress tensor inserted on that. Okay. So this was, as you say, as we saw, the state was.
Sorry, just about Abhijit's earlier question.
Yeah.
Suppose we had put some boundary states at the ends of the cylinder, where they were thought of spatial.
Yeah.
And then modular transformed that to get some effective state to state amplitude. You would have still got the same answer.
Yeah. I would get the same answer.
So it's not very sensitive somehow to it.
Yeah, we'll get the same answer if you put.
Suppose I had a cylinder and I put some boundary states. Then I want to, and then so that's my path. I put some boundary states here, and then I put the insertions.
Finite cylinder. Finite cylinder. Yeah.
And then I turn it around. Now I'll interpret this as some state, transition amplitude to some other state with this insertion. And if you can argue that the energies of things that run here are what he has, you would still get the same answer. Because the whole thing is just running of the minimum energy state over a long time. Yeah, that's right. Yeah, the lowest state. Yeah. But let's see, this is how we actually found. This is by like calculation, some more direct calculation. So we want to calculate this, okay, just to probe the energy of this particular state, right? So so if you remember, the definition was something like some kind of thing here, and then there is an insertion here, and then I'm doing a trace k. Okay. This, of course, if you bring it here, it's essentially the and you sum over the i's. It's basically this, evaluating the stress tensor in that particular beta phi state, okay, which is this. It's essentially this correlator. Okay, evaluating this is essentially evaluating this correlator. Okay. Now this correlator is trivial to evaluate because you can use the ward identity to evaluate the correlator, and so using the conformal ward identity, I guess people know this. You just have to, you have to use the fact that the stress tensor has a Schwartzian to evaluate this particular thing. I think people know this. Related to the 2 points.
Yeah. So basically, T phi phi is delta. If it's on the plane, Z1 minus Z3 to the power maybe 2, Z1 2 delta minus 2, and Z1 minus Z2 to the power 2, Z3 minus Z2 to the power 2. This is the correlator. Okay, and then of course the stress tensor on the cylinder, there is a Schwartzian which transforms it. Okay, and if you just evaluate that.
And so suppose I want to make this manipulation on a finite cylinder, I would need to put conformal boundary conditions at the end.
A finite cylinder.
Suppose I want to regulate your
regulate
for a moment.
Yeah.
I have to put some boundary conditions. To respect conformal invariance.
Yeah, they'll have to. Yeah. Conformal boundary.
And as long as it's conformal boundary states, this will just go through.
This will go through. Yeah.
The mapping might see that.
This mapping. Yeah.
No other detail of the state is needed. Other than that.
Yeah.
Right? But if you have a finite cutoff, then your mapping from the cylinder to your plane might see that cutoff.
You mean this mapping? This one. This mapping makes the plane, plane into the cylinder. I use that, Yeah, you'll have to. It will become a more complicated. So, so this is how it shifts, because this is the this delta phi comes from here. from this, evaluating this, and the Shortchen gives the other thing, right?
I'm a bit confused.
Yeah.
The way you have presented it, it looks like it really
Yeah.
looks like a chemical potential for translation, and the
Chemical
effective chemical potential is kept fixed. Your beta by L is like the chemical potential.
Beta by L. Okay.
Because
Yeah. Beta is like Hamiltonian chemical potential. I mean, you can think about that.
Good chemical potential for translation. Oh, I see. Because one is twisting. Now I see.
right.
Yeah.
And then the effective chemical potential is beta by L, which is kept finite as L is taken to infinity.
Yeah.
So
Yeah.
now the final answer, I couldn't find. What
Yeah.
was the final answer for temperature? Yeah.
This is the shift. Yeah. So this.
There is neither. Okay, there is no dependence on L.
Yeah. There's no dependence on L.
How do you
Yeah.
write it?
Because in this calculation, for instance, the L doesn't come, right? I mean, for instance, example in this calculation. Yeah. Yeah. Because it's just beta. I mean, if at all there is an L here, there will be an L here, and there will be an L here. Yeah. So the effective temperature shifts actually, and in fact, it's quite. It looks counterintuitive, but it looks like if the delta has positive conformal dimensions, okay, the temperature, what happens to it? It decreases. It decreases if it has positive conformal dimensions, and it increases if it has negative conformal dimensions. It looks a little, but if you think about it from the free energy point of view, actually the free energy for positive conformal dimensions is exponentially suppressed, and that's sort of the way it translates it. So it looks, it looks counterintuitive, but this is how it comes out.
But shouldn't you think about it as that you are using their formula for a different state? So their derivation heavily use the fact that you are in thermofilter, let's say, which is like tiny.
But you will see that the temperature of this theory is still beta. We will come to it soon. The temperature of if you look at the first law, okay, you want to calculate, look at the.
First law we'll see beta will multiply energy.
It will be beta.
But I believe effective, the combination that goes into it, it will be Hamiltonian and some sort of a translation operator that will multiply beta by.
Yeah. Well, I mean, effectively, okay, in many probes that temperature behaves like this, okay, but not all. Not all, actually. We'll see that it's not all probes. For instance, you want to calculate the free energy, calculate the entropy, and then you find what is the first law. Okay, we will see that soon. The first law is still beta.
Multiplies energy will be beta, not beta phi.
No, energy also, you see, beta phi squared. That's what we computed. Energy is, this is what we computed right now, the stress tensor. Okay, so the energy is some c pi squared by.
In the new state.
Yeah, this is all in the new state. Yeah, this is the new state, T phi.
From the perspective of old state, this energy will not be exactly energy. It will be a combination of energy and some translation.
Well, I mean, I just inserted the stress tensor on that particular state.
In the new state, it is the energy.
Okay. Yeah, so c pi squared, this is how the energy.
Right, one more question,
Okay. Yeah, no, it's okay. This is confused us a lot.
Yes.
Okay.
Suppose I think of finite, I do my modulation. Then it seems very important, at least intuitively, to get the answer that if you take your boundary state and then act on it with your primary operator, then the state that you get afterwards has no overlap with the vacuum.
No, well, yes,
Because otherwise, then you would get the old answer.
Old one, it should.
And why is that always the case?
Yeah, that.
Because this is actually.
It shouldn't transit into a vacuum and then we get the vacuum. So, but this is a primary with a vacuum. I mean.
But a boundary state is a complicated object.
Complicated,
Maybe I don't understand the boundary states very well, but
so you're saying boundary state, then I insert this fellow.
And then why can't there be some amplitude to get?
And then somehow this feature of the vacuum shouldn't transit.
Should not appear
in this slice.
Thing. And is that somehow automatic from conformal invariance or some special condition on the boundary state?
I don't know.
I know you don't think about it because you don't read.
We just.
However, if I insert, say, I insert the things that finite minus L by 2 and plus L by 2. But my actual, I'm saying that you can put a little bit of another infinity of evolution. Let's say there are two cutoffs.
So another infinity of evolution.
L prime, and you insert this guy's the phi at L in such a way that L prime is still infinitely larger than L. Then it will be like phi acting on vacuum
Vacuum and
then overlap of that with that
the vacuum. Yeah, you can push that guy too far. It's possible. Yeah.
Depends on how,
Yeah.
how you
Yeah. Actually, this is sort of the calculation prescription we will be arriving at. See, if you want to calculate, various, probe this particular state with various objects, with various other operators, we'll have to evaluate correlators on that particular, with the phi and phi at infinity.
Sorry, and when you actually do the calculation, is L being taken to infinity or is kept fixed?
In this calculation, the for instance, this calculation, this calculation, we'll have to push this to infinity. Because the correlator is a complicated object, and you have to normalize, and all these grow like that, and they cancel in an appropriate way.
Okay.
And we have to take that to infinity. Yeah.
Sorry, phi is local operator?
Phi is a local operator. Yeah.
So why don't you get test clustering
Yeah.
zero?
But this one, but the energy is somehow sensitive to this. I mean, just by the simple calculation. I don't know. I mean, clustering. It's.
Why should we go everything to zero as a power of 1 over 8?
Yeah, so it's doesn't. I mean, okay, maybe I can show this calculation because it's very simple. I mean, the calculation. It's essentially because, so you see, when you go into the cylinder, for instance, this, you would think that, when I push this to infinity, all this vanish, right? But we are dividing also, you see, you're dividing by these norms. Okay. Yeah. So you're dividing this by that, and then you'll get that. The normalized thing. Yeah. So okay. So it's peculiar that nobody thought about it, but this particular thing. And okay, if you want to evaluate the entropy of the particular state, we evaluate it this way because we want to do it independently. So we evaluate it this way, and again, using the behavior of z tau, you can evaluate this z tau asymptotically. You can plug it inside, take the Laplace transform, and you get this particular answer for the entropy. Okay, and you get this answer for a particular entropy, and in fact you can verify that ds is equal to beta d because we evaluate the energy and beta det. So it's actually first law is obeyed with beta. Okay, and so beta phi is only an effective temperature which is suitable to describe certain observable, and effective temperature is suitable to describe certain correlators of light operators. Okay, so that's what we are going to look at. So we are going to create this particular state, and this particular object is heavy, and then we are going to probe that with various light operators. Okay, so that's what we'll do. Yeah.
Don't quite see the torus.
Yeah.
If there is an interpretation in terms of torus, then why shouldn't one be able to?
Yeah, but maybe the thing to think about it is, it's like very large L, but with a finite boundary. I mean, maybe one can think in that. Okay, maybe the torus. Yeah, that's not a torus. Yeah, but then how to use the modular? Yeah, that's what. But there is this independent calculation, which is what we will do. This one, for instance. Yeah, which also gives the same answer.
Sorry, I just one more question on Gautam's picture.
Yeah.
If you take Gautam's picture and then put it
Yeah.
back on the disk, then your operator insertion is not quite at the center.
Okay.
Because there's a long infinite tube. That's
Right.
the end of that is the center.
Center. Okay.
So I just want to make sure that is it true that there's no overlap? Because
It's one
Yeah.
point function. It's a 1 point function on the plane.
Yeah, that doesn't have an
But
overlap.
there's no overlap.
Yeah.
Just translation.
Yeah.
Descendants will have
Yeah.
5.
Right. Yeah, it's
The thing that still
Yeah.
seems odd to me
Yeah.
is that you're putting these from this time interpretation.
yes. Yeah.
That you're putting two local operators
Yes.
and you're getting extensive change in the
Yeah.
solution. That
It's,
sounds very odd.
yeah. It's some. Yeah.
Yeah.
Yeah. I mean, it's energy density. This is energy density. Yeah. This is energy density.
Two local operators.
Yeah. That question of says it's okay. All these are suppressed certainly, but when you divide it, I mean, if you divide it by this.
Yeah, that's the calculation.
Yeah.
The net interpretation
Yeah.
is that the effective energy, for instance, of the
Yeah.
state is changing in an extensive way, right?
Extensive way, yeah.
Normally, you will think that you need to integrate that operator over the line to get that energy.
It's related to this very far away.
Yeah, but very far away, you would think it is suppressed. It's suppressed. But all those, in the calculation, it just, it's quite surprising actually.
And you have not taken large C anywhere yet.
No, this part is just anything. And it's very surprising people just didn't calculate this, right? I mean, it's just a calculation of the energy density of this particular thing. You just take this 3-point function, push these guys to infinity, and evaluate it on the cylinder. I mean, pragmatically, that's like the calculation. It's quite surprising, actually.
But strictly speaking, if they are local operators, energy is not conserved. You are perturbing your theory.
Yeah.
By coupling, which only is like a quench.
It's like a quench, yeah.
So what do you mean by energy? Some kind of average over the
Yeah.
beta or what?
This energy, this T, okay, right now here, it doesn't matter actually what position you measure this in.
So
It doesn't matter.
Remember
It doesn't remember that. Because when you push this to infinity, all that goes away. The point at which it is inserted, it doesn't count actually in that simple calculation. I mean, if you want, we can go through that very simple calculation. It's, This is ZZ, WW, you have to sum them. You have to sum WW plus WW bar with a minus sign. That's the tau translation. Because I knew this. If you want, we can go through that, like very simple calculation. But I think the calculation is okay. But just to deal with
the question, suppose we take these operators and smear them over time. Keep them localized in space, but smear them over time. Would anything change?
Smear them over time.
It will take your attention away.
Yeah, it doesn't change. The calculation, if you smear them over time, it doesn't change actually. It doesn't change. Because when you push this to infinity, the tau doesn't matter.
Right.
And the tau is over the finite part of it. It doesn't matter.
It sounds so strange, right? Just do it one point, then
Yeah.
the point is very far away and this changes the energy.
It's
Sounds so strange.
I don't know. I mean, but it's surprising. Nobody it's a simple calculation. You can smear it. I think it doesn't. It won't change the result. You want me to do the calculation?
No.
It's like, It's,
This way also it's different, right?
Huh?
You measure the energy.
This way, that will be the difference, I suppose. I don't know, TZZ minus TZZ bar, or, I mean, tau translation is that, no? Like tau.
Yeah, it is, I mean, the difference.
And tau, sigma might be like with a minus sign, so that will cancel. But if delta and delta bar were different, maybe it will.
We would have expected that to be changing, right? Because
This, I don't know, tau. This is what is sum, You sum it is,
Please say again.
I mean, you have this picture, right?
Yes.
Yeah.
You have this cylinder, large
Yeah.
cylinder, you have inserted some T,
Yeah.
pies here, and you are measuring T.
Yes.
But measuring energy going which way? Going this way or going this way?
Right.
So this could change, it seems, because there is,
Something.
it's stated it will
Yeah.
change considerably.
Yes.
But this will not. But here it's this that is changing, while this is 0.
Really? I thought he was getting his whole effect from the fact that this was changing. I mean, from
Yeah.
your intuitive
Yeah,
calculation, it was when you cut
Yeah.
the change.
But-
Subtract this TZZ minus TZZ bar.
T tau is what we measure,
Uh-huh.
which is TZZ plus TZZ bar. This is what we measure. Z plus TZZ bar.
But now you do minus, and then you get cancellation.
TZZ plus TZZ bar.
But which one?
Yeah.
I'm
Yeah.
Is this the energy? Yeah, which way is this the energy?
So this, if you, so it's okay. Let's do this way. So it's 2 pi by beta. All right, 2 pi by beta, and this is the map. Okay, sigma plus I tau. Okay, sigma plus I tau. So, so if you look at the map, it's let's see, T tau tau is del by del tau z del z, my z and tau same, del z by del tau z T z z. Okay, so this is the way. Okay, plus T del tau del z bar by del z bar. Del tau T z bar z bar, right? So T z z and T z. So when you differentiate this, you know, there is an I which comes from here. There is an I which comes from here, and there is the same I which comes from here. Okay, so you will have to add them up.
Therefore, T tau tau is what you're getting.
Yeah, T tau tau is what I.
And tau tau is this small circle.
Yeah.
Which is what.
Yeah. Sorry. yeah. Tau. I also got it. Tau is this one. Tau is this one.
Okay, so it's this energy that is.
Yeah. Tau is that one.
Now the other identity is not changed.
Yeah. Not changed.
No issue.
Yeah.
But then how did the free energy change?
Yeah. Free energy. Okay.
Path integral change, right?
Yeah.
Energy doesn't change.
Okay.
I think of path integral as energy plus some entropy. So is entropy what's going on?
Yeah, entropy also changes. I mean, if you look at the entropy. Yeah.
But even entropy should change in an extensive way.
Yeah.
Something else.
Entropy density is what changed. Yeah.
Entropy density change.
Yeah. This is entropy density because 1 by beta. So entropy density changed. So yeah.
Okay, so you just push the problem.
Yeah.
Okay.
Yeah.
But if you don't smear over time,
Yeah.
there is not a state. I mean, there is not like a soliton. There is more like an instant one, because you are inserting
At a particular. Yeah.
Then the intuition about
Yeah.
extensivity and all, I don't know what,
How,
but
yeah.
of course, if doing an integral and not doing an integral is the same thing, then
Yeah, here, and then there's some beta factor which comes about because it's independent of beta. Yeah.
so then
Yeah.
when it becomes a state, then I have the
Yeah.
same.
Yeah.
There's some words that will
Yeah.
help me somewhere. But
Yeah. Okay. Well, I mean the calculation is like this. Yeah, very. Somehow nobody looked at the other way. You know, that's the problem. Everybody's looking at it time this way, and we just looked at it this way. In fact, you know, the way we arrived at it is also quite because we were seeing these puzzles in the holography. We'll see when we. I don't know whether I'll come to it. Okay. Okay. So. So 2-point function in a heavy state now. Now basically our calculation recipe is this. We insert this at plus infinity minus infinity, and then we evaluate these particular correlators, light correlators, and these are evaluated at thermal cylinder beta. Okay. So and if because if let us also assume that the order of these operators, I mean the dimensions, as I said, as we discussed before, all those arguments were for any delta, but now we go for large C delta, the delta of order C, and we just evaluate these correlators using the monodromy method. That's a method of evaluating these correlators, and then you can transform that correlators from the plane to the cylinder by this map, and
all Euclidean so far, right?
All Euclidean actually. All Euclidean, and here's the correlator on the holomorphic part of the correlator, just that, and here epsilon L, here it is. These are the light fellows, and this is the heavy guy, and that same structure comes here even, and then if you evaluate it, this is the answer, okay, of the 4-point function. Normalized 4-point function, and you see that it effectively looks like the light operators are evaluated at a new temperature, okay, which is beta phi, which is shifted by this beta. So the light operators do this. Yeah.
So it's coordinate, and
Z is this coordinate. Yeah.
so here you are just taking the leading contribution of the OOP.
This one? No, okay, so there is this method of evaluating, two light operators, okay, so 4-point function of two light operators with heavy operators, 4-point function, okay, and with nothing exchanged, okay, when we do that. It's called, so there is called a monodromy method of doing this, and this is the answer for the correlator.
Sorry,
Yeah, but in the large C limit, so let me. Yeah, Virasoro block. Yeah, just the Virasoro block. Just the Virasoro block. Yeah.
Virasoro block going from 0 to 5
5 to 5. Yeah. That's why I said the vacuum block. I said a vacuum block. Yeah. So that thing.
So this is large C result.
Large C result now. Yeah. So this is the answer. So then we.
Wait, sorry,
Yeah.
Just to
Yeah.
understand that. The two things intuitively that don't seem to be fitting for me. One is that if you just had 5, you weren't getting a vacuum running.
Yeah.
And the second thing is that you're looking at that's consistent with your way of
Yeah.
evaluating.
Yeah.
That
OP between OO.
yes.
Yeah.
And take only the contribution of the Virasoro block.
Yes.
Yeah.
And that's the answer.
Yeah.
And this Virasoro block is like a vacuum block.
Yeah. It's a vacuum block. Yeah.
But that's consistent with the fact that vacuum is not the vacuum does not contribute to when the phi's go very far away.
When the phi's go very far away.
Suppose I didn't have the O's. I just took the 2 phi's.
2 phi's.
I
Yes.
thought the reason you were getting your answer was that the vacuum didn't run in the middle.
The vacuum didn't run in the middle.
Okay.
Yeah.
And so it's consistent to get then an answer.
You're right.
That's not
Yeah.
inconsistent, right?
I can't also see. So we are putting the phi's, okay. Yeah, and the phi, okay, and then the curly this one. Yeah. Yeah. So yeah. Okay. So yeah. Let us go. Yeah. So we evaluate it, and then it looks like okay. So this beta is shifted by this temperature, and then so this demonstrates at least.
Yeah, it's a different thing, right?
Yeah.
Because you're just saying that 5 thing.
Yeah, 5 thing. Yeah.
Phi doesn't produce.
Yeah. 5 thing. Yeah.
It's not connected.
Yeah.
And,
So-
and you're allowed, even though these guys are in the middle and the phi's are at the edges, you're allowed to do this vacuum blow. It doesn't.
Yeah, you're allowed to do that. Yeah.
Even though that's
You're allowed. But if the phi's are put closer to that fellow, closer to the infinity, then you're not allowed, I think.
But I
Like-
thought the phi's were very far away and the O's were.
Phi's, that's what. But suppose we want to take this limit, for instance. I think when we want to take this limit, when these guys are also separated and going closer to those fellows, then the O's are getting separated and going. Yeah, then the other OPs come in, I think.
And why are you?
Yeah.
Are you trying to? This is valid because you close the OP the other way around somehow.
The other way around. I mean,
Meaning, you have your 2 phi's far away.
far away. Yeah.
Naively, the 2 O's are in the middle.
Middle. Yeah.
So if you were very naive, you would do 1 O with 1 phi and another O with the other phi.
1 with 1.
Because these are 2 nearby.
Yeah.
But maybe you could think of it somehow the other way around. So phi are near to each other and O are near to each other. Is that the?
Yeah. That's what I'm thinking. The O's are near together, and the phi's
Phi's are near from the other side.
other side. Yeah. Some.
But then doesn't this require?
Yeah. No. But not. It's just we push that to infinity. I think that's all.
You mean just a cylinder with 4 operators. 2 of them are at infinity, 2 of them are at
Finite.
which are close to each other.
Yeah.
Now you can for convenience you can map this to a plane where these close operators will remain close, and then
Yeah.
you just have 4 operators in a plane with 2 operators being close.
Close.
And cross ratio wise, this is the thing that will dominate.
Yeah.
And those will automatically be close to each other.
So it sounds to me like what you're saying is that these 2 operators are here on the plane. One is at 0 and one is at infinity, right?
Yeah.
So now you're saying that there is a way of, suppose I thought this is the Riemann sphere, there is a way of putting a disk which captures 0 at the other end of the Riemann sphere but doesn't.
It's possible to do that.
I mean, the 2 operators could be at close on the Riemann sphere, and these guys here would still do the OP.
Yeah, that sounds good.
But if this answer is analytically conformed to Lorentzian signature, then you have to come back to justifying why you kept only the identity. Like, why this channel is justified.
And it sounds good to me if you can make a Riemann sphere. Suppose it was an annulus, is this still true?
It's not Riemann.
Well,
Okay. Oh, I see.
but this is true.
That's
Yeah.
Because it's not
because it's
Yeah.
you got
There's a
a
whole
Yeah.
the cross
Yeah.
ratios.
Then you can close it the other way.
Yeah, the
That's
way.
what's worrying.
Yeah.
curve.
Okay.
Because there could be,
Yeah.
you know,
Yeah.
these configurations not relate to each other by conformal symmetry.
Yeah. Okay. Let's go ahead. Okay. So then, so this is equivalent to this. Then we can do it for the 3-point function of light also, but I wouldn't give you the result. But what we want is actually 4-point function of heavy, and then the light operators, 4 light operators. Okay. But there is a hierarchy of the light operators which I will use. Okay. Here. So we have these guys. These guys are always there, and we are probing them inside all the time. Okay. Yeah.
So this wouldn't work even if it is a torus, right? Even if it is a torus.
Torus. Yeah.
It's not
Yeah.
compactification.
Yeah, you need to put 2 guys at infinity. We need that actually.
Why would it work? Couldn't I cut the torus into one bit and the other bit? Suppose I had 0055.
5.
And
Okay.
I cut one part of the torus with the 5 and the other part of the torus.
Yeah.
Yeah, but the OP would be, you know, going this both ways. Kind of. I mean, it's not the standard.
Yeah.
It's not a sphere. It's not in this.
Yeah.
It's a torus.
Yeah. It's a torus OP.
That's true. That's true. Thank you.
Yeah. Okay. So we can do this for the 6-point function also, because we need this for the OTOCs actually. We'll see that. Okay. So 4-point function. I wouldn't go into the 3-point function. We can do that also. But essentially we use monodromy methods for this particular thing with this hierarchy. And here's the answer. Okay. So there is these heavy guys, very ultra heavy fellows, and then there are these guys in between. Okay. 4 of them in between, and this is the answer. Okay. When we take this particular, so this is the answer. There is a particular answer for it. Actually,
How is this being
evaluated.
not evaluated, but what are the operators that are dominating this?
Yeah. So there is this heavy fellow here.
Okay.
Okay. Then there is this 4 fellows, and there is a hierarchy actually. Like HL prime is bigger than HL, and so on. And then you can actually get this correlator by thinking of monodromy methods.
Draw a tree graph with
Yeah.
2 things colliding.
Yeah.
And then going
Yeah.
to
Yeah.
two
Yeah.
things colliding.
Yeah.
What two travels in what lengths?
So, for instance, all of them are vacuum blocks.
I see. So
All of them
oil,
are OL prime. Yeah.
And then so you get now 2 vacuum
Yeah.
blocks. They collide now and
Yeah.
produce again a
Vacuum block. Yeah, all of them. So I will tell you this like method of doing this. Maybe that will make it a little bit more clearer. In fact, this answers which we get from here agrees with some other people's also. But let me I had written it down.
know which OP channel dominates.
Yeah. Just hold on. So the way to do it is actually a little tricky. I mean, I had this. I wrote this somewhere and now it has gone away. Just hold on.
I just want to understand this.
Yeah. Just hold on. Yeah. Let me just tell the procedure so that it will be clear. I've lost it. So the way to think about it is the following. Actually, is it's like suppose you have a theory at temperature beta. Okay, that theory at any arbitrary temperature beta. That theory can be thought of as and you want to evaluate. You want to get correlators from there for large C correlators from there. You can think of that as actually inserting heavy states at temporal infinity. But heavier than delta, 24 by C. I mean and you create that particular state. So you, so let's see that. So you think of a 4-point function. It's a trick actually. Think of a 4-point function of a theory at temperature. Some beta hat, okay, and then that beta hat can be thought of
Maybe this is a correction on top of.
Yeah. That's a correction on top of that. It's a correction on top of that. Yeah, and then you map this to the plane. Okay, you map this to the plane. Okay, so then you have these fellows also sitting there. And then you evaluate 4-point function with that insertion, and then again go back to another temperature, arbitrary temperature beta. This is like a systematic method of doing this actually, of getting this answer.
Oh, I see. So
Yeah.
So you are saying
Yeah.
the dimension
Yeah.
of y is of order of central charge.
Central charge, yeah.
Also dimension of OL prime is also of
central charge, yeah.
Oh, I see. So you
Yeah.
do that and then
Yeah.
again include
Yeah,
OL prime.
yeah,
and
yeah,
then-
yeah, yeah. Yeah, there is a
OL are light.
OLs are light. OLs are light.
But what is this hierarchy between prime and observable?
Yeah, well, yeah, because somehow, the hierarchy, yeah, it's like, because we think of this original state, okay. So the original state, how to create this particular original state. So we think of that as first, because that is the most heaviest state, and the rest is lighter than that. Yeah, this is a method. In fact, there was an alternate way this was done, okay, and our answers agree with that, okay, but I'll come to it soon.
But is it the composition map?
Yeah,
You know,
when you do the
correct by
composition,
phi,
yeah.
there is some beta going to beta prime.
Prime,
Then
yeah.
you correct by OL prime, the beta prime goes to beta
Double prime, yeah.
Is it effectively replacing delta phi by delta phi plus OL prime?
Delta? No, it doesn't do that. It's multiplicative. It's multiplicative. Yeah, it's multiplicative. Yeah. So.
You don't have phi insertions. You are just calculating it at finite temperature beta. No
Mhm.
phi insertion.
Yes. Yeah.
Then this is like keeping the identity block, let's say in this
Yes.
two channels.
Yeah.
And then that compute, even to have that computation reliable,
Yes.
there will be a time scale which will dictate that this form of the answer is valid up to some scrambling time, which will be determined from validity of the OPE. So I was assuming here you will this answer will be valid, but in Lorentzian sequence there will be a domain.
There will be a domain in
There
it.
will be a
Yeah.
domain where it is reliable, and beyond that you need.
Yeah, and it's that domain only we need it actually. Yeah.
Yes,
Yeah, that's it.
that
Yeah.
should
Yeah.
come out.
Yeah, because there was another alternative method of doing it, doing the calculation, I think by Sonner and everything, Sonner and group, and they also have this particular domain. I mean, it overlaps with their domain actually. Okay, so let me, so there is a way of doing this, and let me just go ahead. Okay, so essentially, this is the thing. Essentially, what happens is that going over the cylinder, thermal cylinder again, finally, this is the answer for those insertions. It's basically the temperature gets shifted by beta phi. Okay, so this is the answer for the 4-point function. And HL prime is the other fellow, and alpha prime, that cross ratio part has this alpha prime, which is the other heavy state. Okay, so now we have these things. Okay, and the result is so basically. Roughly speaking, if you want to evaluate correlators in that particular heavy state, it's like shifting the temperatures. Roughly, that's what we are seeing. That's the picture we have. And we can use that to probe various things. So first is Rene entropy. Okay. So if you look at Rene entropy and evaluate this, okay, these are light operators. These are genuinely light operators. And you calculate this, use that formula which we have for this 4-point function to calculate it. You get this particular answer. Okay, and here you see, here it is. It's like the result agrees. This, like if you evaluate the Rene entropy in a conical defect, you essentially get this. If you make this transformation, you get the answer for the conical defect. So this is the formula for that. Okay, the answer.
Positivity of Hilbert space, you have some set of inequalities for entanglement entropy. Presumably, the domain in which you have negative norm states, you will also violate those inequalities for entanglement entropy.
Negative norm states. Yeah. So so if this delta is negative, we'll see. So we'll see it in. I can see it only in the OTOCs actually. Yeah.
Also
yeah.
because you have it, you can just take those inequalities are satisfied or not. There are
Some.
bunch of inequalities.
Okay. Yeah. Okay. One can see. So let me. So in fact, here there's a counter check. Okay, a counter check with this answer for the entanglement entropy. If we look at the short distance expansion, okay, of
entanglement of what with what?
So basically, we have this state, okay, and then we put in the twist operators in between, and we just evaluate the 4-point function.
So this is now you take an interval of 0L.
0L, yeah.
And that with the rest of the system.
With the rest of the system. Yeah, we just probe that with the rest of the system. And since these are light operators and these are heavy, we use that formula.
Yeah.
We use the formula.
And L is kept finite.
Finite, yeah. L is finite. In fact, here, this is where when L goes to infinity, there's a problem.
Okay.
there's a problem with this thing. This L, this L, this L. So this, so for instance, if you take this answer and do a short distance expansion of this guy, okay. So we know from general analysis the short distance expansion, if there are no other states, low-lying states in this, that the leading terms are the stress tensor. Okay, you plug that fellow inside here. Okay, so essentially you will have, if you do the short distance expansion for it, okay, so there is the first term and then there's the stress tensor insertion here. That means the stress tensor phi phi, which you have evaluated already. Okay, so that's what comes inside. Okay, and you can take this big answer which you have and do the short distance expansion and see if it agrees with that. Okay. And of course it does agree. I mean, the short distance of this we get with this particular shift. Okay, so the sign hyperbolic actually shifts. The argument in the sign hyperbolic shifts. So in fact, when there is no delta phi, it is just a pi L by beta, but there is this shift, and that shift is matching with this, with this particular short distance expansion. Okay. So again, the OTOCs now, the OTOC. So this fact, many people.
The last thing is true for general operators OL, right? Not just sigma. Any sigma OL will also produce T.
Yeah, it will produce T. But this H sigma is that weight of that particular twist operators. That is a particular fact of that, and that's how. Yeah, I think this fellow comes out completely. H sigma is the same as which comes out. Yeah. So the OTOCs, okay. So here I think people don't know, I mean, it might not be familiar with many facts. The OTOCs, to evaluate OTOCs, it's very similar to a quench process actually. This, many people might not be very familiar with it, but
you can
yeah.
heat a string of operators on some down state, on some background state, and then you can study quench in that state.
Quench in that state, yeah.
You say at some time slice, you have down state, you hit with bunch of local operators.
Okay.
So this is the new state in which you want to study some quench problem. Probably it will map to that somehow.
No, I mean this. See, OTOCs has a 4-point function. There is a particular ordering and everything. There is an epsilon limit. There is a particular cross ratio goes to 0 in a particular way, and then there is a branch cut and so on. Cross. Yeah. So that same thing happens in something called a quench process. I mean, it's exactly the same phenomena of seeing the OTOC in another way. Okay. Exactly the same thing. So I'll tell you that way, which is much more, at least for us, because we discovered it this way. So for us, it is sort of more. We were. Yeah. Yeah.
What's the n going to 1 formula that you get? I mean, I remember the formula.
C by 3. Yeah, C by 3.
So there we have some log, and then there inside the log there's a CH.
Yeah.
So you were saying that
you just expand this out. Yeah, you just expand this out. So log, and you expand it short distance.
Yeah.
Okay. So sign hyperbolic. Yeah. You get this. Yeah. You just expand it. Yeah. You just say, yeah. So the OTOCs, I mean.
And did you talk about observable doesn't see beta prime but sees beta?
So for us, I mean, of course, beta. This just thermodynamics. Thermodynamics sees beta. It's just thermodynamics. And of course, in these large C problems, of course, if you're sensitive to 1/C corrections, you would see it actually. But that's a more complicated thing to do. But because all these correlators are large C correlators.
But you are keeping 1/C preliminary to see leading behavior, leading theoretic.
No, we are not keeping 1/C. It's all large C. It's large C.
But you are taking away the disconnected part in some sense.
Yeah, the disconnected part is taken away.
First connection to disconnected. Then this is the one that shows you the behavior.
Yeah, first connection. Yeah. So we're keeping large. Yeah, it's large. It's all, even the bulk you can see this actually. Okay. So. Yeah.
You're saying that entanglement entropy sees this new temperature.
Yes.
But thermodynamics sees the old temperature.
Old temperature.
So
therefore, in the large L limit, right, this won't go into thermodynamics. Because one of the things about entanglement entropy is that if you take the large L limit, for instance, it should give the full thermal entropy.
But there is this context in which
Yeah.
in which the entanglement entropy thermalizes to the thermodynamic
Entropy.
So there is really the
Yeah, entanglement entropy, the conventional thing is that when you take the large L limit, because the whole interval is now taken over, it goes into the thermal entropy. It goes into the thermal entropy.
I was saying something different.
Okay.
I'm saying that at some, let's say you have some finite
L,
like
okay.
you have, and then there is this entanglement entropy goes linearly and saturates. When it saturates, that value is the thermodynamic entropy.
Okay, this is a different thing.
Here, however, it seems that it does not saturate to
I don't know the time dependent process. Yeah, we have to see. It's it's saturated. Yeah, I don't know that.
Something interesting.
What is the state initial variance? One local operator?
Some boundary state, modified by. I mean, the quantum points can be modeled by some class of states, and in that there is this this linear saturation theorems, and in that the saturation thing is
Sorry, just
I
missed this bit. You're saying entanglement entropy is given by this temperature with this square. And thermodynamics wasn't also. I thought thermodynamics was also given by the same temperature.
Thermodynamics was given. There was this, but I think it didn't have a square root. You see. So let's see the thermodynamics. No, you take the large L. Large L. So you get something like is n plus 1 by Cn. Okay, that doesn't matter. So C log of this guy. So n equals 1. We have to put 1 C by 3. Okay, and then we take exponential of that, and log of the exponential. So it's alpha phi pi L by beta. Okay. But if you look at the entropy formula, and alpha phi has a square root. Square root. And look at the entropy formula. It doesn't have a square root.
But
it doesn't have a square root.
The free energy, there was a beta squared and the same factor?
Yeah, free energy there was a beta squared.
And the same factor. So free energy was modified by the same square?
Squared, yeah. Free energy was modified. Like let's say free energy, let's see free energy. Or the energy, for instance, Free energy has a beta squared.
Okay.
And
So but if I just compute it?
Yeah. And the energy also has a beta phi squared. Okay. But the entropy doesn't have that.
Wait, if I take free energy and I use thermodynamics to compute the entropy.
Free energy, Yes. Yeah, I think it will come, it will come out to be this. Yeah, we did that also,
Right.
Yeah.
But what is just the standard entropy but with beta replaced by beta by square root thing?
But no. Yeah, that's the reason we did an independent computation of the entropy. Yeah.
Because you differentiate.
Actual temperature. That's the reason we did an independent computation. We were very confused actually. Okay.
In that sense, it's fake, right?
Yeah, it was not really.
Yeah.
It is actually normalized.
But this.
Everything to be denormalized temperature, then everything is in.
Then you would you will have to understand this formula, density of state formula. Then,
In a way, isn't it better just to think of it as the coefficient behind the free energy changing rather than a change in the temperature?
You can think but the thing is that many of the correlators which we are effectively calculating, it is good to just replace it like that, and you get the answers actually.
And this is what you said right in the beginning, that it seems unnatural because that's like renormalizing C.
Which you don't do it.
I mean, this way of understanding, because this is really the black hole microstate, right? I mean, if you think in terms of a calculation in some state with some temperature, right? But instead of that, you can model it with insertions of heavy operators, as you were saying.
Yes.
So without starting with temperature to begin with, just on the sphere.
We can model it.
At the pole, north and south pole, and all the correlators will see as if you have compactified it with
Right.
So in that sense, isn't it the same as doing a calculation?
All certain operators, but if you insert more of them and so on, or if you insert like if you go 1 by C corrections and so on, you will see it. You will start seeing it actually. It's in that sense. Okay. So this quench, I mean, this thing about connecting OTOCs and quench is, OTOC is basically a 4-point function. There is some ordering and there is some cross ratio. We have to take its small limit and so on. But exactly the same thing happens actually in this particular physical question actually. And that's how we arrive at OTOCs. It's basically, if you consider an entangling interval, okay, and you create a pulse. You can create the pulse by inserting a primary at something like I epsilon minus I epsilon or so on. You can create a pulse like that actually, because if you create a primary at I epsilon and another primary, not that big primary, another primary, and if you measure the stress tensor, it looks like a pulse moving around. Okay. So then this pulse moves in. Okay. So the pulse splits and it moves on the light cone and it comes inside. Okay. And the entanglement entropy jumps here. Okay, when it gets into the light cone. This phenomena, if you calculate this jump or whatever, this correlator is exactly the OTOC correlator. Okay. So that is the way we actually get the OTOC. I mean, we actually calculate the OTOCs in this particular manner, and you'll see. Yeah.
These two operators,
Yeah.
extra operators, they
Yeah.
are at some time slice and they are separated by some distance, or that doesn't matter.
Yeah, they're separated by this complex time. We put them at 0.
To regulate this IUPL.
Yeah, it is actually to make the width of the pulse finite. Yeah.
So apart
Yeah.
from that, you can separate them in space. As
You can do that. You can calculate that. You can get the butterfly velocity. So
Butterfly velocity, yeah, that is
I mean, whatever. Yeah, you can get those other things. You can say.
and the time scale. So what
Yeah.
is the time scale here? So for example, there is a time scale where you see this OTOC giving the chaotic.
Yeah. So this is at L1 and this is at L2, and then you evolve it at time t. Evolve it to time t.
Right.
Yeah.
So if this pulse goes outside of L2, like crosses
Yeah.
this interval, then presumably it will again go down.
Go down, yeah. But the thing is that you have to stay within inside to see the OTOCs. You have to stay within inside and be on the next sheet.
Be on
The next sheet, because when it goes inside, it goes into the next sheet actually.
Who goes
Next sheet, yeah.
And so the time scales maps are, so if I take L2 to infinite, let's say I don't want the
That's another
then
way.
I can
Yeah,
easily
yeah, that's
go
another
down.
way to do it. Yeah, that's how. Yeah.
That is the speed of light.
Yeah, that's the speed of light. Yeah, because things evolve in speed of light in this conformal theory. Yeah, it evolves. Yeah.
Because signal is
Yeah.
supported, signal is
Yeah.
supported only on the right.
Yeah,
Right?
signal is supported on the light. Yeah.
Because somehow this is 4-point function of 2 plus
Yeah.
2 meters and this
Yeah. And this the heavy. But then we are going to. Yeah.
like how it is and how this time on.
Yeah, sure. That's because of all these I epsilons and so on, and you take a particular cross ratio. Yeah, it's we see that, we show it actually in one of our papers.
Statement
Yeah.
doesn't care about 2 dimensions. The fact that there is this mapping, the mapping of OTOCs to this
The quench process.
Mapping probably doesn't.
Yeah, it shouldn't. But how will you calculate this in
Right,
higher
the
dimensions? Yeah,
calculation, the
yeah,
particular calculation with twist
Yeah.
operators cares about
Yeah.
2 dimensions,
Yeah.
but the mapping probably
yeah,
doesn't. Right?
yeah.
Is this true?
Yeah. I think you can. This quench process is the same kind of process, but yeah. And of course, we don't do it just at finite temperature. We do it now in that particular state.
Right.
That's what we do actually. We calculate it in that particular state, and that's what I described here. And the jump can be evaluated using that, and this allows us to study that OTOCs. And here is the placement actually. These are the various placements of these operators. It's a little involved, but it places and the cross ratio behaves in a similar.
In large C, in this quench problem,
Yeah.
is there a holographic description? Presumably there is a holographic description to calculate entanglement entropy from the bulk itself.
Yes, yeah.
And on the other hand, we have some description for calculating OTOCs in the bulk
Yes,
using software. So
yeah. But it's the same actually.
is it the same, or
Similar.
is there some mapping problem already?
No, it's the same process. Yeah, same. Because the correlators just get mapped to correlators. Yeah. The large C correlators just get mapped into this. Yeah. So the operators are placed in a particular way, and there is this evolution. And okay, basically, I'll just tell you the results, and OTOCs and are calculated. And the things is that there are various scalings you'll have to do to go into those OTOs limits, and that you can actually interpret it in the quench process also. Basically, the energy density of this pulse, I mean, the energy has to be finite, so you have to scale the operator in some particular way, And when you do all that and go into the branch cut, into the second sheet, and here is it, is the answer. Okay. And of course, in this particular case, all of the temperatures get mapped to the different temperatures. Okay. It gets mapped into the different temperatures, and that's the idea of, because that's why I went through the process of calculating the various endpoint functions, and it gets mapped into different temperatures, and of course now it is obvious to see that this is bound.
Such a quench problem is an OTOC problem, therefore it has to satisfy this bound.
Yes.
That should tell me something about entanglement entropies. And does this map to some known?
Yeah, so there are ways to get the bounds just from the quench problem also, because the entanglement entropy should not become complex or infinite or something like that. Using that also we have got, for instance, the previous bound when I said about the, the higher spin 3 bound, we got it that way actually.
To understand it. So the fact that you have some entanglement entropy which has some very simple bounds, like it cannot be complex.
Oh, okay, those bounds. I mean, those are what we are using. Yeah.
But the fact that problem can be mapped to an OTOC problem.
Yes.
And for OTOCs we know some bound, which is this. For example, the derivative at some bound. That should say something about the entanglement.
Yes. Yeah. It is the same thing. It's the same. Same statements can be made. At least for that particular correlator which we evaluated with the charged, higher spin charged state, it led to the same kind of conclusion that the bound on the charge.
Of entanglement entropy inequalities, or there are suitable derivatives which you can try to prove by itself from entanglement entropy side.
Okay. Yeah. Okay. So I mean, hopefully, it's this is the conclusion. But then I'm going backwards. Yeah. Oh no. This is the jump in. So you are asking the analogous question, entanglement entropy, and there is a jump in entanglement entropy, and that also can be calculated. Everything shows the shifted temperature and so on. So basically, we have shown that if a large theory admits a large state of large negative dimension, this fellow violates the bound. Okay, so is this realized? Is this setup realized? That is the whole thing. Is this setup realized? And so there is a particular theory. In fact, we actually were studying this particular theory, and we had to go and derive all those things, at least understand it in this way. Okay, and it was really like, the way to get it from here, it's very hard because it's a factor of 2 difference. Okay, I'll show you why. Okay. So Polyakov Bershadsky, is basically a Chern-Simons. It's a Chern-Simons algebra, and it's like a bosonic n equals 2 theory basically. So there is this Virasero. There are these currents, plus and minus. There is a U1 charge for that current. Okay, and this is a U1 current. And so then, these are the weights basically of that, and this particular thing commutes rather than anti-commutes. Okay, that's a particular Bershadsky-Polyakov algebra, consists of spin 3/2. This is one of the first higher spin sort of some weird spin algebra I think they were looking at, and this global part of this algebra can be got by a different embedding of SL3. Okay, if you look at the usual SL3 where people study higher spin 3 theories, it's this L0, W plus minus, and W0, and the L's algebra. But if you do this identification, this is how you can get the W32 algebra. Is basically L0 hat is half of this, and this is actually W, while this. So there is a way of realizing it just from using SL3. Okay, algebra matrices, SL3 generators. There's a way of realizing this, and of course, therefore, there is a Chern-Simons theory dual to this thing. You can construct a Chern-Simons theory based on this algebra, and that's the bulk. Okay, and so first let's consider the simple BTZ-like solution in that. Okay, so essentially we have this L hats, okay, L hats, and there's this turned on by some W minus 2. So this is the BTZ-like Chern-Simons connection. This is the BTZ Chern-Simons connection. So there is a similar dictionary of the level of the Chern-Simons to the central charge, and so on. Okay, so we use the L hat instead of the usual SL2, but we just use that. So this is a BTZ connection embedded in the SL W32 algebra, Chern-Simons theory, and we impose holonomy the usual holonomy, but with beta. Okay. The usual holonomy of the BTEC connection, that when you go around the thermal circle, it should be a identity connection along the beta. So you impose with a beta, actually. That is another important thing. We impose it with beta, and then there are some conditions, and the stress tensor can be read out by looking at the W minus 2, because W minus 2 is constrained by this holonomy condition, okay, and therefore the stress tensor can be read out by this thing, and this is the stress tensor. Now, this differs from the usual one by C by 6. It differs from the usual one. And then if you use our formula, its delta is minus C by 8. Okay. That's like, I mean, it's a factors of 2 actually. We were like really confused whether we are making mistakes or so on. It's factors of 2. So C minus C by 8. And then we can try to probe it further, use the holographic entanglement entropy prescription. And Devor and Jotar have given this prescription of evaluating Wilson lines and evaluating that. And in fact, they have also said how if there is spin 3 by 2, how you have to modify that. And you can calculate that.
So what was why this Bershadsky thing?
It's that we don't know, right? We just calculate this. We look at the BTZ connection. Okay, we use usual holonomy along the thing. So it looks like a BTZ. So I would imagine that I would get the usual thermal energy of the BTZ black hole. But when we evaluate it carefully, we don't actually.
No, but you said delta equals C by 8.
Yeah. So if you match it, sorry.
If you match it, yes.
Yes.
But a priori, what is that?
That state. Yeah. So there is some state in the vacuum.
But can you calculate its delta match and see that it's actually C by 8?
In the representation theory, for instance, we have a discussion about such states exist in the large C limit. In the representation theory of the W32, okay, negative dimension states exist. Okay, but this fact that in the holography I just calculate this, okay, and this is the vacuum which we find is just there. I mean,
why is it that what this holographic vacuum that you have corresponds to
this particular delta? If you just take the Chern-Simons and calculate it with the usual prescriptions, I mean, this is what you get actually. Yeah, it's quite.
So you're going to say that the square root is half.
Yeah, because delta is minus C by 8. So if you plug in that formula, where is that formula? It was something like this, no? Square root of 1 minus 24 delta by C. So 1 minus plus 24 into C by 8, 1 by 8. So this becomes 3, and then 1 plus 3 is 2. I mean, it's quite amazing, yeah.
Non-unitary phenomenon.
No, it's not a non-unitary. Yeah, it's not a non-unitary theory. Yeah, it's not a.
But just like C minus C over it, there could be other states that whose deltas go as C, right?
But if you analyze the vacuum using representation theory, this is the state which comes about actually. Yeah, that's what we also see that. Yeah. I'll have more things about the representation theory soon. So minus C by 8. And then if you use the Wilson line prescription, okay. So there's a Wilson line prescription of evaluating the entanglement entropy, and in fact, if there are half integer spins, there is a particular normalization of the Wilson line, and you have to do all that actually and calculate it. We get this particular formula, okay, which is different from the usual one. Okay, pi L by beta versus 2 pi L by beta. Okay, and then again, it will match with our formula of the square root of 1 minus 24 delta by C. I'll have more things about this entanglement entropy formula soon. So that matches with this. And a small check in the interval size, okay, if you do the small interval expansion, of course, it will match, and it gives you the thermal entropy. Not the thermal entropy, that expectational, the stress tensor by doing this.
Sorry, are you still thinking of this theory as being effectively like a cylinder with operators inserted at
this particular, for us it's just a Chern-Simons theory right now, okay, and we just follow the rules of the Chern-Simons theory, okay.
But if you imagined it connecting with the previous discussion,
I would imagine it is some operators inserted, I would imagine, but I don't know how to do that. I mean, like really see it, we just go through the rules of the Chern-Simons theory. I mean, we just go through the rules, and I'm getting these results actually. So
But do you get naturally that the operators are local?
yeah, well, we don't even see that. Like we just see it in these observables. Yeah, yeah. We don't see all that. No, we don't see that. We just calculate these observables, like energy density, entanglement entropy, and so on. We just see, and then we see the differences between the usual BTZ black hole. We don't see it. Yeah, we just see there are differences. These factors of 2s are off, and so on. And then.
But in the BTC black hole, you have some cigar.
Yes, yeah. So that, yeah, the geometry, yeah. So that geometry is imposed because it's Chern-Simons theory. I mean, these are Chern-Simons. So we don't use the geometry. We just use the holonomy. So that closing of the cigar is this one. The holonomy in the time direction should be just unity. So I mean, that's the generalization of that particular, because it's higher spin theory. And then we just use that. We just use this condition.
Is your space a circle?
Is the phi?
Yeah.
Yeah.
You're looking at field theory at finite temperature on a circle?
Finite. Yeah.
No interval here.
There's no interval, yeah.
So this is like the torus that Abhijit gets.
Yeah. Yeah, in the bulk it will be like that, yeah. But in the bulk, I mean, we actually don't, there is this phi, of course, and there is this temporal circle, and there is this phi, but we just, we just do it, yeah.
To the boundary, that will be a torus.
There will be a torus, yeah. Yeah, there will be a torus.
If you can do exact computations, you will have more information in some sense.
Huh?
If you can do exact computations,
Yeah, if you have
this effect of things coming back in the space direction.
Yeah. Okay. So let's do the Wilson line. So the Wilson line also changes this, and of course this also checks with that. And in fact, we have generalized this entanglement entropy a little bit further. We looked at not just the BTZ-like solutions, but there is like more general solutions, of these particular cases. Like for instance, this is a more generalized black hole, like higher spin versions of that. Okay, so these are different connections. They satisfy the flatness condition, and then and the holonomy conditions give these. And there is basically they have spin 3/2 charge. They have U1 charge. It's a more general class of black hole-like solutions in this particular theory. And we calculate the entanglement entropy, and of course at the q is equal to 0 limit it matches this. But there is it's a more complicated actually formula. And in fact, there is a bound which we got from the entanglement entropy, and that also can come from the representation theory. I am not discussing the representation theory very much here, but there's a bound which came about from this, which also we got from representation theory. And if another thing from this more general formula, which actually again matches, is that so this object is not just the BTZ, it has the Q charge and so on, U1 charge and so on. And so if you evaluate the short distance expansion of it, you would expect, by the Sugawara, the J also has stress tensor. And in fact, this combination, if you expand that entanglement entropy formula, this combination which comes about is precisely that combination of stress tensor and J squared, which decouples from the U1. Basically, usually if you take the usual U1, Tj is equal to non-trivial, but this combination is what decouples, and that's precisely what comes about here. So that's a small check about that. Okay. So again, you can evaluate this holographic OTOCs and using this, usually the quench kind of description. This basically there is this heavy state which falls into the black hole. So here it is that vacuum, that non-trivial vacuum, which is like the BTZ but non-trivial. And so there is this heavy state which falls into it. And you can use that kind of picture to evaluate the OTOCs and in the Chern-Simons language. And you can do that. And of course, so there is first you have to create the conical defect, which is the heavy state, and there is a connection for that, and you go through that process and evaluate the Wilson line. And indeed, of course, I just want to say that finally the correct jumps. The jumps are exactly like as though what we saw in the CFT. Here's the OTOCs and so on. So this is the formula, the Lyapunov exponent here too gets corrected. But this is mimicking the basically, this whole Chern-Simons language just mimics the large C results actually. but it was good because here, this is a particular realization for a very definite delta phi. Okay, one should maybe do more non-standard embeddings of higher Chern-Simons theories to see if such phenomena are there. Most probably, such phenomena is there. Okay, so maybe I can just conclude that Perlmutter at one point of time basically showed that an infinite tower of higher spins, if it's a finite tower of higher spins, there is a violation of the chaos bound. But in particular, higher spin charges have this associated Lyapunov exponent. But here we see a different mechanisms at work, basically existence of this weird ground state. Okay, so I'll stop. Thank you. Yeah. Yeah. Of course.
A different mechanism at work
Yeah.
can also mean the non-realisation.
Yeah, I mean, basically in this theory, the Cauchy-Schwarz inequality is, not true. Because,
But here, even if it is true, it is biological, right?
in this one, in these higher spin theories,
Even
this is a different, this is a different mechanism. That's what I think. I don't know. I mean,
Isn't it somehow the statement that a unitary theory cannot have a finite number of high spins? Because the derivation just uses unitarity.
derivation of
Schenker central.
They use unitarity. Meaning they use Cauchy-Schwarz and at least Cauchy-Schwarz they use.
So they get a result. Then independently, if you put a high spin, of course it will validate. So I think the logic should be that if you have a unitary theory, you cannot have a finite number of high spins.
So from that unitarity is not clear from the bulk point of view.
That is not clear. It's not clear from the work.
I have one comment about the earlier part. The thing that was confusing me about this extensivity was my stupidity about upstairs versus downstairs.
Okay.
So, you were putting insertions of phi downstairs in the path. Now, of course, because you've got these two phi's separated by length L, there's a correlation function which is e to the power some
exponential suppression.
Okay, but had you put it upstairs, that exponential would have got exponentiated.
Upstairs means,
suppose you had changed the action by j phi. That's the thing that would have been corresponding to changing the energy. That exponential would itself have got exponentiated and would have been a very small change in the energies. So I think it's this upstairs versus downstairs.
Meaning in the path integral versus explicitly putting it.
At least this was confusing me. I was thinking I'm just changing my action by some small change far away. That shouldn't change the energy. And I think it will not change the energy. But what you're doing is taking just this thing and taking the first part of it. Because you're putting it downstairs. And you're taking the whole series, it would be actually I don't know if anyone else was being confused.
No, but it was very confusing for us.
Downstairs changes the.
It's like, suppose you have an e to the power minus, suppose your change is e to the power small parameter epsilon, j, whatever it is, times e to the power minus minus n. Okay, so this is a very small thing. But if you take
why e to the minus n?
Because it's a correlation function and no, but because of the mass gap somehow at finite temperature.
Correlated go as
theories effectively have a mass gap in Euclidean space.
So I think that one over L after the exponential math will become because that's a 1 over L function. And now you're doing the exponential thing, so it will presumably become some 1 over inch L or something like that. And that will be
The mass gap occurs when you rotate to the Lorentzian. In real time, then you see a decay of the correlated real time.
Even Euclidean space.
Into that.
Take n equals 4 angle theory. Take it at finite temperature, the theory has a mass gap. All spatial correlators decay exponentially. This is why hydrodynamics works. I'm sorry, this is why the hydrodynamic partition function works. It's local partition function.
Here, of course, it's obvious because it's mapped to the plane, plane to the cylinder.
But let me just say, for instance, under dimensional reduction, this is the statement that 3D QCD has a mass gap. At least in generic theories, this is true. I think that's why this is the exponential, which may be the same thing as what Gautam was saying in technical language. So that's the exponential. But now, if you take this exponential and put it upstairs, that's a very small change.
Yeah.
But if you just want a 2-point function, you take the first term in that.
First term.
And that exponential then adds to the action.
Yes. It shifts
That,
the action.
that's the, I think, mechanism. I mean, technically.
But it's, it's like, it's surprising that, it is surprising because it took us a long time to actually,
I would really like to hear the whole talk once again.
The connection with the second part is a little bit of a magic, because when you write down the SL3 connections, I would have expected that the appearance of this phi fields at the end somehow would create a conical.
But I think in the bulk, in the thermal, if it is like that, it's a conical defect.
Yeah.
But in this holography, I suppose if you have a vacuum, and somehow that should be the solution, right? You're describing things in that. Like suppose a thermal state. If you're looking at thermal, just the usual thermal state, it will be the BTZ black hole.
Yeah, then you will have the
BTZ black hole.
and so on.
So here also we just try to do the thermal state first.
Yeah.
We try, we use the correct holonomy for the beta holonomy. But then when you evaluate the stress tensor and so on, and the entanglement properties of those is different. It's with the scaling thing. So then we are interpreting that vacuum solution to be that.
Doesn't it say that instead of taking the SL3 connections that you were taking actually, you should take some new guys in which you have L minus 1 minus blah blah blah, and then you don't insist on the Cigar condition.
So that's a different, it's a different state maybe. If you don't want that particular state.
But you do have some phi's sitting.
That is what that's what we want to find. Like what we did naively was try to do the BTZ black hole in this theory, and then it has these different anomalous kind of properties. So it is not the BTZ black hole. It's something which is more. Which we are interpreting as this particular vacuum.
I'm suggesting another way of connecting. That instead of using these connections, use a connection with conical defects.
The conical defects are usually temporal. Somehow you want to put it. These are conical defect is usually temporal. We have it actually a conical defect, because we need to make it fall inside this particular solution. It's temporal.
That's not a conical defect in the
in this particular time. Okay.